Thank you, Professor Kim, for your kind introduction. And this is I'm very glad to be back to KAIST. I visited KAIST almost more than 20 years ago, when it was very new at that time, I think. And I spent a month in Korea at that time, in early 1990s, and it was my starting point of exchanges with Korean mathematicians. And after that, I received an excellent student from Korea whose name is Jeon Byung, and whose name I never managed to pronounce until now. It's very, very difficult, this pronunciation for the Japanese. But he was an excellent student and also a very nice person. So I'm glad that he came, and I'm glad that he is now an important mathematician in Korea. And I want to learn now from him about variational problems and geometric PDEs. Okay, so today I'm in this series of lectures, I will talk about front propagation in reaction diffusion systems, and I will explain what it means. But my slides were prepared for conference talks, and I tried to change that. I didn't know that most of the audience are graduate students. So I will also use the blackboard later, but I will start with the slides and add some additional remarks to some pages which I didn't give enough explanations. And also the name of this conference, it is KAIST CMC Math Biology Conference, but in the program which Professor Kim gave me, it was written at the Biomath Mini School, so it is part of the mini school part of the conference, I suppose. So I'm giving a very short mini course mostly to graduate students. So this is the outline of my lecture, but I will change it as a matter of fact, so please don't just neglect it. But the important thing is the profiles of propagating fronts, the meaning of which I will explain soon. And okay, let me just, okay, so this is what I originally intended to speak. But I will change a bit and explain more on the first subject. So profile of propagating fronts, I will explain what it is. But in some reaction diffusion equations and systems, you can observe spreading, propagation of a front. Front is, in this context, the area where the solution changes its value very, very rapidly. So you see something like a wall, and it is moving outward. And this is called spreading of front. But in more general context, it is called propagation of fronts. And what is the nature of this propagation for reaction diffusion equations? So this is the main subject. And I also wanted to speak briefly what happens if the medium is not uniform, not homogeneous, but ergodic. But this one, I'm not sure if I have enough time to speak about it. I will speak more on the periodic medium, in which you can establish a lot of precise mathematical formulas. Much is unknown for ergodic medium, but I might briefly mention it later. And the next one I may also mention little bit about two-dimensional cylinder, front propagation in two-dimensional cylinder whose boundary is oscillating. And this, if I have time, I will also mention this topic, but mainly I will focus on the first topic. So this is the cylinder with undulating boundary. So if the boundary is not flat, what sort of effect does the geometry of the boundary give to the propagation of the front? So this is the third topic, and I may explain a little bit about that. Okay, so outline of my talk. Okay, this again, I may change a little bit later, but mainly I will talk about first part is the introduction. So what it means. Expanding front and asymptotic shape. I will explain its background. Then I will have some analysis, mathematical analysis of the speed of traveling waves and also spreading fronts for KPP equations. I will explain what KPP equation is. And this much of the mathematical analysis will be given to this second topic. But in this second topic, I will focus on the situation where the environment is spatially periodic. And then finally, I will talk about spreading front in two-dimensional periodic medium in which the spatial inhomogeneity has a stripe pattern. And these can be, I can explain mathematical details of these two subjects. And to understand, okay, this is the fourth subject, but I might skip this fourth subject, but I may explain briefly. So to understand the second and the third topic, one needs to first know the basic properties of the principal eigenvalues and the principal eigenfunction of certain elliptic operator. It is mainly one-dimensional, but the difficulty here is that the operator is not self-adjoint. But nonetheless, there is a variational formulation of the principal eigenvalue and eigenfunction, and this will play a very important role in the estimate of the speed of traveling waves in the KPP equation in a spatially periodic medium. So I will focus much of my talk on the explanation of this subject. Okay. Now let me start some introduction about the front propagation. So why people study this? And I have to say something related to math biology, because this is a math biology or biomass mini school. So let me start with a well-known example. This is a classical story, spatial spread of muskrats in Central Europe. And the muskrat is an animal like this. It is originally from North America and did not exist in Europe. But someone brought this animal, just a few of them, to Central Europe, and eventually it spread over Central Europe. It's a familiar story. This kind of thing happens in every country, and we are suffering from many species brought from America, but Americans are also complaining that some fish brought from Japan are killing the local ones, because the environment is different, and those alien species can be stronger than the local ones. And then the ecological system will change dramatically if you bring such alien species, plant or animal, and famous recent story is Australia, where there used to be no rabbits, but someone brought rabbits in Australia. And 20 years ago, when I visited there, they said that there are 500 million rabbits compared with only 20 million people or something like that, 20 or 25 million humans in Australia. But there are more than 20 times as many rabbits, because they don't have any enemy. There is no predator for rabbits, so the numbers are not controlled. So this is how the muskrat spread. It was brought to Central Europe in 1905, and gradually it spread. And it is well studied how it spread, and it is in the paper here. And this was, since the Central Europe, as you see from these contours, there are mountains and rivers and lakes and valleys, so it's not uniform. It doesn't spread uniformly, of course, but if you measure the area of a given year and make a square root of the area, then it is not a circle, but nonetheless the square root of the area may give some sort of average radius. It turned out that this average radius grew linearly in time, which means that in some sense the spreading speed was more or less constant. And this was studied by Skellam in 1951. So this is the same picture, more or less, and here is Vienna, and this is Munich. So why you have this kind of straight line? This is the real data. So this Skellam proposed a model to study this. And as a first step to understand this phenomena, he made an assumption that animals just move randomly, like a Brownian motion. And of course, they mate and reproduce, and also die. So there is a growth rate. So new offsprings will be born, but also some older ones may die. So there is growth. And also each animal just move randomly. This is a simple assumption. And under this assumption, he studied how, if this were uniform, homogeneous, how the boundary grow. And if it is completely homogeneous, then the boundary is a real circle. And he just calculated and showed that the boundary grow with constant speed. So this is roughly an explanation. Okay, there are two simplifications. First, he assumed that animals move randomly like Brownian motion. Because of that, you get the diffusion equation. And second assumption is that the environment is spatially homogeneous. But actually, Central Europe is not a homogeneous area. There are many mountains. But as a first step, this was a good analysis. And he justified this by his theoretical studies. A natural question from the mathematical point of view is that what if the environment is spatially inhomogeneous? What can we say about the spreading of this territory? And this is one of the main topics in my talk. So to study this kind of phenomena, Skelam used a diffusion model. So diffusion equation has this formula, this form. This is Laplacian. And then there is a growth term. This part is genuine diffusion. It has the same form as the heat equation. In the case where the dimension is equal to 1, you have this equation. This kind of equation also appears in many other contexts. This is a context in mathematical ecology, but it also appears in chemical reaction or physics. For example, Skelam's paper was published in 1951. So ecological study using reaction-diffusion equations. But in 1952, two other important papers were published by other people related to reaction-diffusion systems. One is by Alan Turing. His paper, the title is a chemical basis for morphogenesis or something like that. He sort of conjectured that the formation of many geometric forms of a body starting from a single cell, which is symmetric, but there's a symmetry breaking. This was done by some chemical pattern within the tissue. And this chemical chemical material was not identified at that time, and he called it morphogen or morphogen, and he assumed that it satisfies. Okay, it's not like animal, but it's a small molecule, so it exhibits random motion. So it is governed by this kind of equation. Actually, it's a system. There are you need at least two components. And he used the term reaction-diffusion system of reaction diffusions in his paper. So he's the first one to claim that morphogenesis, there is some reaction diffusion mechanism behind morphogenesis. Well, the story about the Turing is a little more complicated because molecular biologists sort of later did not appreciate it so much, and this reaction diffusion system and molecular biology mechanism was found to be more important for certain part of reaction diffusion system, certain part of morphogenesis. But later, people found many examples in which Turing's conjecture was correct, at least in some cases of morphogenesis. But in any case, his work is not limited to morphogenesis, but what he discovered is that diffusion could create instability. Usually diffusion is what makes things uniform. So everything flat will be stable, but a combination of some nonlinear reaction, which I denote by f of u, actually it's a system in his case, combination of this and diffusion can destabilize the uniform state and leads to creation of some non-uniform pattern. So this kind of view itself was revolutionary. So this is really a very, very important year. But again, in 1952, Hodgkin and Huxley introduced a model for propagation of a signal, electric signal along the neuron. So it's called action potential. It is now well understood how the nerve signal propagates, but at that time it was not known at all, and they proposed the reaction diffusion equation coupled with some ODEs. It's called Hodgkin-Huxley model. The smallest, simplest one is written by 4 equations. But again, this is related to reaction diffusion. I write it as RD, reaction-diffusion systems or reaction-diffusion equations. So 1951 to 52, three very, very important fundamental results appeared in slightly different areas. And it had a very, very strong influence on later studies. And what I am going to talk about is the simple model. This is just a single equation. Although I will mention a little bit about the pre-predator model later. But for the moment, let's focus on the single equation. This is the equation which Skellam studied. And then you can show that there is a special solution for this equation called traveling wave. By the way, I will mainly focus on KPP Fisher type equation, this, but I will also mention Allen-Cahn type equation, bistable equation. So what's the difference? So the difference is in the nonlinear term f of u. In chemical reaction, f of u represents the creation and annihilation of new molecules by chemical reaction. So some molecules will appear by chemical reaction, some molecules may disappear. In the context of ecology, which Skellam studied, f of u is the growth of the population. U here is the U of xt represents the population density. Of some species. And here we sort of simplify the situation and assume that the population density, it's a continuum model. So the number of individuals is so large that we assume that it can be regarded as continuum. So then f of u is, in this context, the birth rate minus death rate, roughly speaking, per unit time and per unit area or unit length. And U is not the population itself, but the population density per unit area or unit length. So this is the setting. Then it is known that this equation, for example, for Allen-Cahn equation, there are three zeros of f, but two of them are stable. If you neglect Laplacian u, then du dt equals f of u is a simple ODE. Then u equals 0 and u equals 1 are stable zeros. While in the Fisher KPP equation, u equals 0 is unstable and u equals 1 is stable. And they appear, both of them appear in many areas, even in ecology, or particularly in population genetics both types of equation appear depending on the situation. But in both cases, it is known that there exists a special solution called the traveling wave, which is written in this form: u of xt equals v of x minus ct. So if the solution, this is in one dimension, and if the solution is written in this form, you will know, you can see that the graph of the solution doesn't change, and it moves with the speed c as time passes. So this is the what we call traveling wave solution. It's a special solution, but very, very important. And another important subject is the spreading front. It's a bit different from the traveling wave. Traveling wave is a special solution which moves at a constant speed. But the spreading front is the following. You start from initial data which has compact support and look at how the solution behaves. Then you will observe an area where the value is close to 1, which is stable, stable point of f. So the solution wants to approach 1 as time tends to infinity. So this area is close to 1, and outside there is a transition layer, and outside there it is close to 0. So the area where u is equal to 1, which you can call a territory of some species, if this is in the context of invasion of alien species, which Skellam studied, then you may regard it as a territory of invading species. So how it spreads from a compact support? So this part is called spreading front. Spreading front is a front that spreads to infinity, expands to infinity, and the front region is where the solution, the value of the solution change from 1 to 0 relatively rapidly. So there are two important notions two important notions for front propagation. But to understand spreading front, it is very, very important first to study this traveling wave solution. Traveling wave is simpler because it's a very special solution, but it turns out that the behavior of the solution near the spreading front is well approximated by the traveling wave. So let's start with studying the traveling wave solution. By the way, this is about Allen-Cahn equation. I don't go into the details, but Allen-Cahn equation, which is this bistable type, has a completely different property, different from KPP equation, which I will mention more later. In the case of Allen-Cahn equation, it is known that front or interface between the region where u is close to 1 and the region where u is close to 0, this interface moves more or less by the motion by mean curvature, or the motion by mean curvature with some driving force. And for this Allen-Cahn equation, the original Allen-Cahn equation is when this area and this area are the same, which is called a balanced case, balanced nonlinearity. If you look at minus the primitive of f, w, it is called the potential. And the potential looks like this in the balanced case. So the potential for the bistable nonlinearity has two wells. So this is a double well potential, and the double well potential has equal well depth if the area here and area here are the same. And if the two areas are different, then the potential has unequal well depth. Depending on which type of nonlinearity we have, the interface equation is slightly different. In the equal well depth case, the interface equation is well approximated by the motion by mean curvature. And v is the normal velocity of the surface, n is the dimension, and h is the mean curvature. V equals n minus 1 times h. This is the mean curvature times n minus 1, but anyway, basically it's the mean curvature flow. And if it is unequal, the two wells have unequal depth, then we get this. Mean curvature plus some driving force, some constant. And this is well known, and this was studied by physicists long time ago, and Allen and Cahn studied this problem as a model for some crystal structure in an alloy of metals, two kinds of metals. And in the crystal structure, there is what they studied is antiphase boundary. Inside and outside, the molecules are aligned in an opposite way, and there is a boundary which moves because of the thermodynamic motion of the molecules. And then they derived a model which is this. And they showed that motion is approximated by this motion by mean curvature. In their case, F has equal well depth, so this is the case A. And this formal analysis was later studied by many mathematicians, and at least in a singular limit, where certain parameters go to 0, they completely justified mathematically that the interface motion is precisely this. So this is now very well understood. And so it is in the case of bistable nonlinearity, curvature plays a very, very important role. And this is not the case in the KPP equation, which I will mention later. In the KPP equation, a completely different mechanism moves the front. But in the bistable case, the fact that the interface equation involves the curvature is very, very important, and also in applications, which I will mention briefly later. Although my main talk is on the KPP type equation, but I will mention briefly on Allen-Cahn equation, or more general bistable equation. And so this is actually related, bistable case. So effect of geometry on front propagation. Suppose you have initial data here, and if this initial data is large enough, the front starts to propagate to the right. And suppose you have another initial data here, very large initial data, then the front starts to move to the left. And which direction is faster? Front propagation to the left or the front propagation to the right? And in the past, when I gave a talk, okay, this slide is taken from my conference slides. I talked about this in several conferences in the United States or Germany and France. And 90% of the audience had the wrong answer. Professor, okay. So I don't want to test test the organizer or my former student who are already established. And but in the past, I asked some established mathematicians, and they had a wrong answer, 90% wrong answer. So many people thought that, okay, what's the difference? It's not symmetric. If you move to the left, look at the boundary. It has a small opening angle and a big closing angle, and so gradually opening and quickly closing. And here, it's quickly opening and gradually closing, quickly opening and gradually. So many people thought that if you try to move this way, you may be hit at this place. You will have more friction. And if you go this way, the friction is not that large. So moving rightward is faster, is the answer of 90% of the people. Actually, 95%, I would say. And but some people who are very, very familiar with diffusion immediately gave a correct answer. But so far, I had 3 people who answered correctly. So this is faster. Why? As I said, in the bistable nonlinear diffusion equation of this type, where F is bistable, this is monostable. Okay. Later, my main focus will be on monostable case. And in the special case, it's KPP type. And the bistable is this. In the bistable case, as I said in my previous slide, the motion of the front is more or less governed by the curvature. Why curvature? Because if you look at the energy associated with this diffusion equation, for this diffusion equation, the energy, free energy is this. This is the energy, free energy, and the solution wants to decrease its energy. But this energy is concentrated on the front. Where it is flat, okay, I'm talking about the case where W has equal weight depths. So the flat part has the same potential, flat part, but okay, sorry, I'm talking about this case, okay. So this part has lower energy. Okay, the difference, there is difference of the potential behind the front and in front of the front. And then also this gradient energy is concentrated more or less on the front. So it is this part is more or less proportional to the length of the area of the front. So the front wants to decrease its length as much as possible, but since it is pushed from behind because of the difference of the potential, it has to go forward. But then look, if you want to go further, here there is a quick opening. Quick opening means that the length of the front is stretched very, very quickly. Then you need a lot of energy here. Here, opening angle is small means that the length of the front is growing only slightly, so you only need a small energy to make it expand. Therefore, there is less resistance in this direction compared with this. This one is okay. This one here, the front is shrinking because of this angle, but here front is stretched very, very quickly. So this is where it gets stuck. Here there is no place where the front is stretched very, very quickly. So in some cases, the propagation in this direction may be blocked, while this may propagate. So this is a very important property of the bistable nonlinearity. And as a matter of fact, there are applications for this. For example, if you look at this is again bistable problem. Before I focus on monostable case. So suppose that in a more simplified situation, the domain is like this. So there is an opening angle here. And the solution front is moving to the right, like this. Then it has to stretch the front, which means that the front energy, which comes from the gradient, has to be increased, so there is a resistance. And this resistance is very big if the opening angle is very large. And this has been well known for many years. For example, in my old paper in 1979, although I didn't say it this way, I studied a problem in which there is an opening like this, and other people also did it. More recently, the same fact was used, for example, in the study of spreading depression in the brain by some group of people in France. What is it? This is the picture of a brain. And spreading depression is where the brain wave becomes flat, so it's very, very bad for the brain. And sometimes, for example, by electric shock, this may happen. So this red area is where the brain is not working. And somehow it spreads. It's not how much is understood biologically, I don't know, but a lot of simulation has been done, not simulation, but experiments has been done. And it turned out that it occurs very easily in simpler animals like rabbits, but for humans, it doesn't happen so often. humans have more complicated brain shape. Then the traveling wave, spreading front, which starts from here, for example, by electric signal, the brain is paralyzed. So this is depression, and it wants to spread, but human brain is so complicated that it gets stuck somewhere like this, while in rabbit's brain is much simpler, and it can easily spread all over. So this kind of study was done. So it's one application of this observation for bistability equation. Okay, let's skip it. Now, so the first talk is just for the introduction. The front propagation in heterogeneous media is what I want to focus on mainly. And one simple case is the periodic medium like this. And more difficult problem is the non-periodic medium. This is, for example, Penrose tiling, which is known to be ergodic. People call it quasi-periodic pattern, but actually, as a function, this pattern is not quasi-periodic in the usual sense. Algorithm is more or less quasi-periodic, but the function itself is not quasi-periodic. It is ergodic. Quasi-periodic is a small subset of almost periodic functions, and almost periodic functions form a subclass of ergodic, uniformly ergodic function, and this is uniformly ergodic. And so to understand traveling wave, for example, in such medium, or propagation in such a medium, a generalized notion of traveling wave is needed, which is the focus of my next talk. And also spreading in ergodic medium is a very, very difficult subject. And if you look at it from farther away in a larger scale, what is the eventual shape of the front? In the periodic case, in many situations, it's well understood. But in the ergodic case, it is still unknown, although there is a conjecture. Anyway, so the eventual shape will be given by the wolf shape. If I have time, I will mention this briefly. But in the periodic case, this is already established. Wolf shape appears as a spreading shape. So I think, let me just show some slides which I will explain in my next talk. But we have to evacuate the room soon. So this is the KPP equation, this one. So I will focus in my next talk on this equation first, and but if I have time, I will explain briefly, because my main focus is for spatially inhomogeneous problem. So spatial homogeneous problem, how many students know it here, the audience? Probably I had better explain what it is. Okay, so let's look at this monostable case. The KPP nonlinearity is a special class of monostable problem. If you draw a tangent line at u equals 0, the graph of f is below this line. So it is a special case of monostable nonlinearity. And the simplest example being u times 1 minus u. And then it is known that there exists a traveling wave. And how can we prove that the existence of a traveling wave? There are many different ways. And in the case of KPP equation, it is known that there exists a minimal wave speed, and for any speed larger than the minimal wave speed, there exists C0 positive minimal. Such that for any C larger than or equal to C0, there exists a traveling wave of speed C. This is known. And you can prove this by various different methods. The simplest one being by phase plane proof. I'm not going to prove it now, but by using phase plane, you can show that okay, it is a spiral here for C equals 0, but for certain C, it became okay, sorry, it's okay, anyway, it becomes let me see. Okay, I will mention it later. In any case, I don't plan to prove it now, but this has been studied by Fisher and in the context of population genetics, how mutant genes spread within a given population in 1930s, and as I said, in ecology, Skellam used this model, used this equation as a model for the invasion of alien species. Okay, I will show that traveling wave is traveling wave solution is, why is it important? It is important because if you start from some compactly supported initial data, the solution front will eventually converge to traveling wave. And moreover, the minimal speed, the minimal one. So I will explain how to prove it in a very, very simple way, how the solution converges to a traveling wave of minimal speed. So this will be the subject of my next talk. Okay, thank you very much for your attention.